Let's begin. All right, so in the last couple of lectures, we have been discussing how to test hypotheses about the beta parameters in our regression model. And in order to test those hypotheses, we've been using properties of our OLS estimates. So the value of the OLS estimate, its standard error, as well as the fact that the OLS estimator under some assumptions follows a normal distribution centered at the true value. So and because beta hat follows a normal distribution, we said, okay, if we formulate a ratio, if we normalize that beta hat, if we subtract the mean and divide by its standard error, we get a t statistic which follows this distribution, right? So the starting point in hypothesis testing is the fact that our OLS estimate, the beta hat, follows a normal distribution centered at the true parameter value. Now, today we want to just conclude. So this is all chapter 4, as you know. इस पे आप लोगों का कुछ भी हो रहा है. So today we want to talk about the final topic in this chapter, which is how do you test more complicated hypotheses. Hypotheses which involve more than one restriction on the beta coefficients in your model. An example of such a hypothesis is my hypothesis is that all slope coefficients in my regression model are 0. So let's say I'm running a multiple regression with 5 explanatory variables. And I am not sure whether those 5 variables taken together explain any variation in my y variable. So the hypothesis is, the null hypothesis is that those 5 variables do not belong in that regression. Their population parameter or population slope coefficient is 0 for each of those 5 variables, right? So the null hypothesis now is beta 1 equals 0, beta 2 is 0, and beta 3 is 0, and beta 4 and beta 5 are 0. So there are 5 0 restrictions under my null hypothesis. If none of those variables actually predict y or is correlated with y, if all of their beta coefficients are 0, then my null hypothesis is imposing 5 restrictions on my regression model. And so, as we will see today, if you want to test hypotheses like this, where you are imposing more than one restriction on your regression model, then you should use then you should not be using the t statistic. You should use what we call the f statistic. So f statistic ki hum baat karenge, that's the last topic in this chapter. But before I go there, let's do a quick recap or a quick introduction to the normal distribution and its related distribution. So this is material coming from the appendix B. If you remember appendix B, it's a probability appendix. It contains probability concepts that you need to learn econometrics. We had previously talked about properties of conditional expectation from this appendix, which we then used in our proof of unbiasedness of beta hat. So there's a section, the last section of that appendix talks about the normal distribution. So even though normal distribution is something that you see in your probability course, it is probably one of the most familiar probability distributions, the most useful applied distribution out there. So our first course, and you can't take your first course in probability without talking about the normal distribution, right? So but normal distribution से related कुछ और families of continuous random variable distributions भी हैं. that you may or may not have come across before. So let's just talk a bit about the normal distribution before we go on to the F statistic and the F test for joint restrictions. Okay. So one feature of the normal distribution, I mean, I think all of you are familiar by now that the density function, so the normal distribution, a variable that is normal, quote unquote. So if we say X is normal random variable, yeah, we can say X is normally distributed. By the way, you might think, where does this word normal come from? Is there an abnormal distribution? What's normal about this, right? This is one of those things where you take a word from English language and just appropriate it for something totally different, like that 95% confidence. What does it mean? Yeah, statistical significance. Iska kya matlab hai? So I think the reason why this particular distribution is called normal distribution is when statisticians started looking out and collecting data. So there was a journal. So statistics is not a very old field. It's like maybe 100, 150 years old. When people started to systematically tabulate data and study properties of different variables, how they were distributed in the data. So one of the earliest things, in fact, I had posted on the Teams a chapter about random sampling, how it started, right? तो उसके अंदर भी वो बात कर रहे हैं कि people went out, so वो colonial दौर था 100, 150, 200 साल पहले, and a lot of people, Europeans who were interested in scientific measurement and collection of data would go out. For example, किसी नई exotic जगह पे आप गए हैं अफ्रीका में, वहाँ जहाँ पे local population को आपने subdue कर लिया है, now you want to understand their social structure and just understand the people that you are governing. तो उसपे there will be an army of social scientists who are interested in studying natural phenomena or social phenomena. And people would go out, collect data कि जो Africans हैं of this tribe, उनकी heights and weights किस तरह से distributed हैं, are they taller than an average European? इस तरह मतलब you come across something new, you start measuring it, right? Systematic. I guess systematic observation and measurement goes back to Aristotle, the earliest recorded person who did that. So it's not just the colonials or the Europeans in that era, but a lot of data was collected about natural anthropometric measurements के आपकी जो मतलब Africans हैं living in this area, उनकी arm length सारे adults की आप collect कर लें उस पर data, and then see कि वो उस data में कोई variation है. Obviously some would be taller than others, so वो lengths की distribution होगी. How do those numbers vary? मतलब is there some pattern in how the arm lengths vary? या skull capacity जो है उसके बारे में there was something mentioned in that chapter. So a lot of these natural biometric measurements tended, like height, the distribution of height in a human population, and they were not just studying humans, they were studying plants and animals as well. So a lot of these measurements tended to follow a symmetric distribution like this. So there will be some members of that population who are short in stature, short in height. There are some people who are really tall, stand out, taller than the rest. And then there's a whole mass of people of average height in between, right? So there are more people of average height than people of tall and short heights, right? So I think probably because this kind of distribution was arising a lot in these natural measurements, biometric kind of measurements, that's why people started calling it normal distribution. So, and anything that follows a different pattern than this has another name for it. So there's a uniform distribution, there's exponential distribution. So distributions काफी सारी हैं. So हम सारी distributions पढ़ने में interested नहीं हैं. We are interested in distributions that we are going to see in this course, which is primarily normal distribution and then a couple of other distributions related. So normal distribution की क्या properties हैं? So one kind of unique feature about normal distribution, it may hold for some others well, is that if you take a few independent normal random variables and if you add them together, right? If you take a linear combination, so maybe multiply them with a constant and then add them, the resulting variable that you get is where x1 through xn are independent and identically distributed normal random variables. Identically distributed meaning have the same mean and variance. So if you take a sum of these variables, that new random variable also follows normal distribution with its own mean and variance, right? So basically, if you add different normal random variables together, you get another normal random variable. That is not at all obvious thing, and that's not something that holds for other kind of random variables. So if you have two uniformly distributed random variables and you add them, the result is not a uniformly distributed random, right? So this is a unique property of normal random variable. Linear combinations of independent IID normal random variables is itself normal. In fact, to see why this is such a unique property, or understand why this is a non-trivial feature, let's actually think about what happens when we add two identical variables. Simpler example which we can understand. Let's say I do two coin tosses, one after the other. So the outcome of the first coin toss is x1, which takes value 0 and 1 with equal probability. x2 is also 0 and 1 with equal probability. Now x1 and x2 are obviously discrete, they are not continuous. But we want to see, so this is a uniform distribution because the probability is equal for both values that it can take. So if I add x1 and x2, right, does my new random variable, which is the sum of x1 and x2, does it also follow uniform distribution? What distribution would that take? Anyone?
Sir, it will follow uniform distribution because these both are independent and uniform. So their expectation would be the sum of both of expectations.
नहीं, expectation की बात नहीं हो रही, probability distribution की बात.
Yes, sir, it would follow.
Expected value of that will be वो आप बात सही कर रहे हो. Expected value of that will be the sum of the mean of x1 plus the mean of x2. That's correct. But we are not talking about the expectation. We are talking about z की distribution क्या होगी. What kind of probability distribution will it take? Will it belong to the uniform distribution, or will it be some other kind of random non-uniform? बताएं भाई, किधर हैं आप लोग? Wake up, wake up. So Minahil, cold call, please.
To make it, yes. Bilal, if you could go on ahead.
Is there only one Bilal? Bilal.
Yes, there's only one Bilal. Ali Rizwan, if you could go ahead.
Sir, it will be normally distributed, right?
Normally distributed. What set of values can Z take? Normal distribution तो continuous random variables के लिए होती है. So ये तो दोनों discrete हैं, उनको add करेंगे तो result will also be a discrete random variable.
Yes, sir.
But the question was what kind of discrete random?
Sir Farhan has his hand raised.
Ji, go ahead.
Farhan, you can go ahead.
Please
Sir, it won't
unmute
be
yourself.
Sir, it won't be a uniform distribution. Rather, it would be some other distribution which would take values with 0, 1, and 2 with different varies of probability.
जी बता दें probabilities क्या होंगी? 0 की क्या
1/4
probability आने की?
1/4, half, and 1/4.
So this is not uniform because it takes 3 values. Uniform अगर होता तो तीनों values के आने की probability 1/3, 1/3, 1/3. That's what a uniform random variable is, right? It takes different values with equal probability. यहाँ पे the probability of the middle value is higher. So the probability of Z equaling 1 is twice the probability of it equaling 2 or 0. So middle value की probability ज़्यादा. So in fact, if you were to plot this, so probability on this axis and values on the horizontal axis. So my individual variables जिनको मैं sum कर रहा था, they took let's call it 1/4, 1/2. So मेरे individual variables 1/2 थे, but Z is 1/4, 1/2, 1/4. Right, so it's the distribution looks like this. And if you keep on adding more coin toss variables, आप coin को toss करते जाएं multiple times, and you add each random variable. Let's say you do it 20 times. So Z is the sum of those 20 coin toss outcomes. In that case, Z will take a set of values which goes from 0. 0 is when all the coins landed tails, right? To all the way up to 20 when all the coins landed heads, right? Again, extreme values की probability कम है. इसकी probability क्या होगी 0 आने की? So if Z is the sum of 20 coin toss outcomes, x1 through x20, each of these variables is dependent of each other and has the same distribution. When I add them, I get a random variable which takes values between 0 and 20. What is the probability of it taking a value 0?
So would it be 1 by 2 raised to power 20?
Raised to the power
20.
G. Similarly, 20 key, the probability that it takes the value 20 is 1 by 2 raised to the power 20. So दोनों extreme values की तो ये probability, and that's a really small probability, right? How small is this? 1 over 2 raised to the power 20. Can anyone tell us without using a calculator? इसकी क्या value होगी? It's easy. It's not hard. 2 raised to the power 10 क्या होता है? 1024. So 2 raised to the power 20 is 1000 times 1000. It's like 1 over 1 million. Right? So this probability is tiny. So अगर आप 20 दफा coin toss कर रहे हैं, the probability कि वो सारे coin toss outcomes एक ही जैसे होंगे, it's either all heads or all tails, उसकी probability काफी कम है, right? But the probability that you will get exactly one head and 19 tails, वो क्या probability है? That's the probability of z equaling 1. What's the probability that z equals 1?
Like 20 times half power 20.
20 times this, right? Yeah. So 1 over 2 raised to the power 20. So R is simply because आपके head हो या tail हो, दोनों की आने की probability 1/2 ही, and because we have 20 of them independent tosses, so 1 over 2 raised to the power 20 तो वहाँ है, but z is equal to 1 कब होगा? When exactly one coin toss is heads, the rest are tails. So how many different ways of getting exactly one head in 20 throws? You could either, the first throw could be heads and the rest are tails. The first could be tail, the second is head, and the rest are tails, and so on. So basically in 20 throws में से कोई सा भी heads हो सकता है और बाकी सारे tails हो सकते हैं. तो इनमें से हर एक sequence की probability 1 over 2 raised to the power 20 है. And because there are 20 such sequences, so heads could be here, it could be here, it could be here, all the way. So we do 1 over 2 raised to the power 20 times 20. So this is the probability for any one of these sequences appearing. And there are 20 such sequences, so we multiply it by 20, right? Or we add this number 20 times, right? So this probability is still very small. So 20 divided by million is still a small number, but it's bigger than this probability. What is the probability that z equals to? You will notice that that probability will be greater than this probability. Why? Because there are more ways of getting two heads on 20 throws than there are ways of getting a single head, right? So अगर आपके दो heads आने हैं तो वो दोनों अगर इकट्ठे एक के बाद दूसरा आ रहा है तो वो इस तरह भी हो सकता है कि the first coin toss is both heads, the rest are tails. So आप इनको एक pair बनाते हैं, right? So इस तरह के कितने sequences होंगे? 19, right? वो pair इधर भी आ सकता है, आखिरी दो tosses पे भी आ सकता है. But that's not the only 19 possibilities. You could get two heads by पहला with a gap of 1. पहला है, उसके बाद तीसरा head आ गया, and so on. So there are many more possibilities. Combinatorically, if you see, 2 heads की in a 20 sequence, अगर आप count करना चाहें कि कितनी possibilities हैं, those are gonna be how many? Does someone know the answer to this counting problem? कितने sequences होंगे with exactly 2 heads? Because that's what we need to replace 20 with. 20 choose 2, which is so in the chat, that's correct. What is this number? This is 20 multiplied by 19 divided by 2. So there are 190 such sequences. Right? So basically, probability that z equals 2 is much bigger. And you will see that basically there are many more ways of getting the middle value. If you are taking a sum, so the basic intuition is कि अगर आप different random variables को sum करें, so that sum obviously can take a range of values depending on what the individual random variables उनकी क्या range है. So इस case में हमारे individual component random variables तो बहुत simple थे, वो 2 ही values ले सकते थे, या 0 या 1. So when we add them, we get a whole range of values for that sum. उस range of values में जो middle values हैं, उनके आने के there are many different ways of getting the middle value in a sum, as opposed to the extreme value. तो extreme value जो है उसके आने की probability कम होगी, middle values की आने की probability ज़्यादा होगी. Right? Whenever you are summing different random variables, there will be a range of values that sum can take depending on what value each component random variable takes. But because उस range के अंदर जो extreme values हैं, उनको आने के लिए हर individual variable की भी वो extreme value आनी चाहिए. So therefore, अगर आपने उस sum की minimum value क्या है, उसकी probability निकालनी हो, तो उसकी probability उसके आने के chances कम हैं compared to उसके average value या middle value क्या है under that range. So therefore, the sum will always take greater probability mass on the middle values compared to the extreme values. In fact, there is a theorem in statistics, which is probably the most important theorem in the whole of statistics, which says that let me write down a sort of folk version of that theorem, which is that sums of random variables tend to follow what distribution? Anyone? So if I'm summing different random variables and I'm interested in finding the distribution of that sum, that z variable, that z variable will tend to follow what distribution? Anyone? Any guesses?
Normal.
Yes. Exactly. So यहाँ पे तो it doesn't look normal, it looks like a triangular distribution because we were summing only 2 variables. So this theorem, why do I say tend to? Because mathematical theorems hardly, so that suggests an inexactness in our theorem. What we mean 10-2 is ke jitne, it depends on the number of variables that you are summing, right? So number of individual variables in that sum. As that number increases, as it continues to increase, the distribution of the sum will start to look more and more like a normal distribution. So this is an asymptotic result. It is saying in the limit, as the let's call this number of variables n. So as n, the number of variables that I'm adding goes to infinity, this distribution f of z approaches a normal distribution, right? So जितने आप ज़्यादा variables add करें उतना अच्छा है, because the resulting sum, उसकी distribution will look more and more like a normal distribution. So इधर इस तरह लग रहा है, but जब 20 को हमने add किया था, उसकी distribution, you know, will look, obviously extreme values की अब probability 1/4 नहीं है. It has become much smaller, 1 out of a million. That's probably here, right, on this axis, and so you get a distribution which looks not quite normal yet, but as you keep on adding more, so it looks kind of more like normal than a simple triangular tent that we had before. And as you keep on adding more variables in the sum, 20 की बजाय अगर 2000 होगा, so it will start to look more and more like normal. So there's a name for this theorem. As I said, this is the most important theorem in the whole of statistics. What is it called? It's called central limit theorem. And in fact, the way it is stated, so you can say this about summing random variables, sums of random variables. You can also say the same thing about averaging different random variables, averages of random variables. So what is averaging random variables? It's the same as the sum, except के sum करने के बाद हम n से divide भी करते हैं, right? So x1 plus x2 divided by 2. Yeah, x1 plus x2 plus all the way up to x20 divided by 20. So that random variable, which are averages of random variables, also tend to follow a normal distribution. और उसकी रीजन, इंट्यूटिव रीजन वही है कि अगर आप रैंडम वेरिएबल्स को सम कर रहे हैं, तो जो बीच में वैल्यूज हैं उनके आने की कई ज्यादा पॉसिबिलिटीज हैं कॉम्बिनेटोरिकली, वो मिडिल वैल्यू की आने की प्रोबेबिलिटी ज्यादा है एज कंपेयर टू एक्सट्रीम वैल्यू. तो नॉर्मल डिस्ट्रीब्यूशन में भी यही है कि एक्सट्रीम पे, मतलब इट्स नॉट नॉर्मल, हमने अभी भी उसको ट्रंकेट किया हुआ है नॉर्मल, तो सो एसिम्प्टोट सेंस में वो एग्जैक्टली उस तरह नहीं लग रहा, बट उसकी शेप जो है, like the bell shape that the normal density has, it will start to take that. Okay, any questions? So this is like the second major property of the normal distribution. कि एक तो normal distribution, you find it a lot in nature when you try to measure different things. So that's why it is called normal. दूसरी property ये है कि a linear combination, sorry वो पहली वाली तो मैंने लिखी नहीं, a linear combination of normal, independent normal random variables is itself normal. So we said कि एक तो ये property is quite unique. You can't say this about any distribution. You can't say this about the uniform distribution. A linear combination, a sum of uniform random variables itself is not uniform, right? So this is a feature of the normal distribution कि उसके different normal random variables को add करेंगे तो result normal ही होगा. Then the second more powerful property of normal distribution is कि आप कोई से भी random variables ले लें. Doesn't matter what distribution they have. They could be uniform, they could be exponential, they could be highly skewed. उनकी individual distribution जो भी हो, अगर आप उनको sum कर रहे हैं या उनको average कर रहे हैं, that sum or that average will follow a normal distribution, right? So not only do we see normally distributed random variables out in the nature, but even random variables which are not normal themselves, when we add them together or when we average them, that sum or that average starts to look like a normal density, normal distribution. So that is the central limit theorem. And notice that this result doesn't say anything here about the type of the random variable that we are adding, because the type does not matter. So वो random variables in our example तो वो Bernoulli random variable था ना, coin toss. But वो random variable की जो भी type है, अगर आप उसको sum कर रहे हैं, it depends on the number of terms in that sum. Our result, it depends on n, but it doesn't depend on the individual random variable की अपनी distribution क्या था, right? So it's quite a powerful result involving normal random variables. It's called central limit theorem. We'll see, in fact, an application of it very soon. To our regression analysis, econometrics maybe हम ये use करते हैं. What else? Any questions about this? About any of these, one or two? Okay. What if you square a normal random variable? What kind of? So you get another random variable, right? So let's say x is normal, and we create a new random variable. Let's call it x. Oh, x तो हमने पहले किया. Actually, normal random variable के लिए convention ये है notation के उसको z हम बोल रहे होते हैं. So let me follow the conventional notation. So let's say z is a normally distributed random variable, and we create a new random variable which is z square. So this new random variable, this is kind of confusing now, follows a chi-square, what we call a chi-squared distribution. But chi-squared is just a name. Has anyone heard or seen chi before? Chi-squared distribution. क्यों जी, किसी ने chi-squared distribution देखी है पहले?
Sir, it is chi-square distribution with how many degrees of freedom?
Hold your horses. Degrees of freedom को भी छोड़ दें. Chi-squared distribution देखी है किसी ने, density function उसका, या have you heard of this name before? How many of you have seen Kung Fu Panda 3? I assume some of you, मेरे तो बच्चे हैं छोटे, I have an excuse for watching these animated cartoons, but I'm assuming कुछ लोगों ने शायद देखी होगी. Highly recommended, by the way. अगर नहीं देखी तो. So there's a general chi in that. So it's not that chi. It's the distribution chi. Okay. So chi-squared की distribution कैसी होगी? It's a squared of a normal. So normal distribution, as you know, is oh, by the way, this is not just any kind of normal, it's a standard normal. So it's a normal with mean 0 and variance 1. So if you think about standard normal, उसका density function क्या है? That density function is centered at 0, taking negative values, positive values, symmetric. It doesn't look very symmetric. Right. So now I'm squaring this random variable. Right. That's what I'm doing. So my variable x is the square of this random variable. What kind of density function should it take? Anyone? So जब मैं z की distribution ये है, this is the distribution of z. Now I'm squaring z to get x. What kind of distribution will x take? What
Sir,
will be the
X
shape?
only have positive values.
Yes. So basically z की ये जो सारी negative values हैं, जब मैं इनको square करूंगा तो ये map होके इधर ही positive side पे आता है. Right? So my density function for x, पहली बात तो ये है कि वो इस तरह की symmetric नहीं होगा, because you know, एक तो वो values उसकी x की सारी positive हैं, दूसरा ये है कि z की सारी values equally likely नहीं है, कुछ values की जो tail में है उनकी probability कम है, right? और जो 0 के करीब हैं उनकी probability ज्यादा है, right? So similarly जब हम इनको square करेंगे तो जो 0 के करीब वाली values हैं उनकी probability ज्यादा होनी चाहिए, जो दूर वाली हैं उनकी probability कम होनी चाहिए. So we will get the density function of x will only be on the positive side. It can't take negative values. So एक तो ये फर्क होगा. दूसरा, it will thin out as we go farther away from 0. So this is how the chi-squared, the density function of x will look like. So that's your chi-squared density function. ठीक है जी. Now you know the chi-squared variable, that how it looks. So what is the relation of this random variable to the normal random variable? So basically chi-squared is a square. उसके नाम में भी squared आ रहा है. It's a square of a standard normal random. In fact, if you sum the squares, if you have different तो आपके पास एक sequence है standard normal random variables का, right? If you have zi, all of them are standard normal independent of each other, और आप उनको square करके sum करें, which might ring a bell. That's the kind of thing that we like to do. We do quite a lot in econometrics. So if we are squaring them and then adding them, so each individual random variable is a chi-squared, and then we are summing these chi-squared random variables. That will also follow a chi-squared distribution with more degrees of freedom than simply squaring one. So chi-squared की density function मैंने आपको show कर दिया. उसका एक parameter है with it only has one parameter, which is called the degrees of freedom parameter. Unlike the normal density, which has two parameters to it, mean and variance, the chi-squared has only one parameter, which we call degrees of freedom. So the exact shape of that asymmetric curve will change depending on the degrees of freedom. Just like the normal density का वो center क्या है और उसका spread कितना है, that will change depending on the values taken by these. Similarly, degrees of freedom के ज़्यादा या कम होने से वो tail कब start हो रही है, कितनी thin है, कितनी fat है, those kind of things will change depending on the value of this parameter. Okay. So in this case, the degrees of freedom will be equal to n, because there are n terms in my sum. All right. So that's the third property. So if you have sum of squared normals, you get a chi-squared. And the usual symbol used for chi-squared is this calligraphic X with a slightly curvy line and a 2 on top for square. Follows a chi-squared distribution. Now, what about the T distribution? We saw that's another distribution that we have seen, but we didn't really talk about its link with the normal distribution. So let's do that now. So the T distribution is a ratio of a standard normal and a chi-squared. Actually, a square root of chi-squared. Let me drop this K to avoid confusion. My idea here is not to be exact, precise, but to just give you a sense of the relation. So if you take a standard normal, divide it with a chi-squared variable, with a square root of a chi-squared variable. So basically square root लेके आपने वो एक तरह से उसको. By the way, when you write a square root like this, if you take square root of 4, what's the answer to this? Anyone? What's the square root of 4?
Plus minus 2.
Plus and a minus 2. Okay, yeah. So मतलब अगर आपके पास इक्वेशन हो x square is equal to 4, तो उसको आप जब सॉल्व कर रहे हो तो you say x, the answer is x is equal to 2 or x is equal to minus 2, because either of those numbers, when you square them, you get 4, right? So but when you graph the square root function, you don't. So let's say you want to plot y is equal to square root x ka graph. You don't plot it like this, right? You only plot the top part of the thing. Why is that? Anyone? So that's how the graph of square root x looks like. Why not the bottom part also? Because when x is 4, you just said that square root of 4 is plus 2 या minus 2. तो मुझे पूरा ग्राफ नहीं शो करना चाहिए. So who said plus or minus 2? Would you want to talk about the graph as well?
So I said, but I'm confused.
Okay, that's okay. It's okay to be confused. So the reason for that is kind of you can say technical reason, the way mathematicians have defined functions. So a function is a mapping from x to y such that you can have one value of x mapping to one value of y, or you can have more than one value of x mapping to the same value of y. So you can have one to one or many to one mapping, but one to many mapping जो है उसको हम function नहीं कहते, उसको हम relation बोलते हैं, right? So we kind of rule out these kinds of mappings from our definition of a function. So when we want to draw a graph of a function y is equal to square root x, we say that's understood, that's implicit without really saying. So अगर आप सोचें तो अगर आपने पूरी मैपिंग ड्रॉ करनी है तो नीचे वाला पार्ट भी फिर उसमें होना चाहिए ना, बिकॉज स्क्वायर रूट ऑफ 4 कर रहे हैं तो -2 का, इफ यू सिंपली थिंक अबाउट द इन्वर्टिंग द स्क्वायरिंग प्रोसेस, तो स्क्वायर करते हुए तो -2 का स्क्वायर भी 4 आ रहा है और 2 का स्क्वायर भी 4 आ रहा है, तो अगर 4 का स्क्वायर रूट ले रहे हैं तो दोनों वैल्यूज, the reason for that is that one to many mappings are not functions as we define them in mathematics, as we use them in calculus. So therefore it's understood कि आपने अगर स्क्वायर रूट फंक्शन की बात कर रहे हैं तो उसके सिर्फ पॉजिटिव वैल्यू की बात कर रहे हैं. So anyway, that was a aside. So square root of chi squared, a point ये था that this particular random variable, the way it's written, chi squared को तो अभी हमने कहा ना कि it will only take positive values, but आप स्क्वायर रूट देख के आप ये ना समझना शुरू कर देंगे ये जो स्क्वायर रूट वाला है कि इसकी पॉजिटिव और नेगेटिव दोनों वैल्यूज आ जाएंगे. मतलब एसेंशियली हमने वो जो नॉर्मल को स्क्वायर किया था उसको अब हम इन्वर्ट करना चाहते हैं. बिकॉज वो इन्वर्ट करें तो नीचे भी फिर स्टैंडर्ड नॉर्मली लिख देते थे, स्क्वायर रूट ऑफ chi स्क्वायर लिखने की क्या जरूरत. सो दिस स्क्वायर रूट ऑफ chi स्क्वायर is going to be हमने पहले जो एग्जांपल दी थी उसमें w was z square, right? So now हम कह रहे हैं कि हमारे पास डिनोमिनेटर में w नहीं है, हमारे पास स्क्वायर रूट ऑफ w, बट हम ये नहीं कह रहे कि हमारे पास z है, बिकॉज दैट्स एन इंपॉर्टेंट डिफरेंस. बिकॉज z में पॉजिटिव और नेगेटिव दोनों वैल्यूज हो सकती हैं. हमारे नीचे जो हमने यहाँ पे लिखा हुआ है ये सिर्फ पॉजिटिव वैल्यूज के लिए, राइट? सो उसकी डिस्ट्रीब्यूशन स्क्वायर रूट ऑफ chi स्क्वायर्ड की भी डिस्ट्रीब्यूशन एसिमेट्रिक ही होगी, सिर्फ पॉजिटिव वैल्यू अलाउड नॉट करेंगे. ओके, so that's what the t distribution, the t random variable is. So it is a ratio of two random variables. The numerator is a standard normal, the denominator is a square root of chi square. Okay ji? How does that fit in with our earlier discussion of the t statistic? So we said hamara beta hat minus the value under the null, which is just a constant, beta h0, right, divided by its standard error. तो हमने कहा था ये वाली रेशियो, सो उसमें डिवीजन तो हो रही है, सो वी आर टेकिंग अ रेशियो. सो दिस बीटा हैट वाज नॉर्मल रैंडम वेरिएबल. इसका मीन क्या था? And if null hypothesis is true, what mean does my beta hat has? What's the value of expect mean beta hat? So our null hypothesis was that beta equals some constant or beta equals 0, right? So हमारे t stat में हम कह रहे थे कि let's subtract that constant c. So beta hat की distribution is a normal with mean c. If the null hypothesis is correct, beta hat is normal with mean c and variance given by the beta hat variance formula, right? ठीक है. So वो beta hat variance formula क्या है? वो है sigma square in a simple regression, sigma square over SST x, where sigma square is the variance of the error term, right? So conditional on x, ये denominator तो is a constant. So So this variance term जिसका हम square root है नीचे standard error is simply square root of variance beta hat. ये जो variance है अगर तो हम इसको डेटा से estimate करें फिर just like beta hat is a random variable, it's a function of my sample xy value, sample data. Similarly, denominator में जो variance आ रही है अगर उसमें sigma square estimated है, sigma hat square है, so then this is also a random variable. Just like beta hat is a random variable, this variance of beta hat is also going to be different in different random samples. It is an estimated thing. And it is what kind of random variable? It is a chi-squared random variable. Because आप sigma hat square को estimate कैसे करें? It's a sum of squared residuals divided by n or something like that, right? So where individual residual is normally distributed, उसको square करके or something. So this variance thing in the denominator is itself chi-squared. उसका हम square root ले रहे हैं standard error बनाने के लिए. ऊपर हमारे पास ये चीज है. So essentially we get this. So that's and I don't need to tell you कि इसकी distribution density function की shape क्या होगी. There's one other thing about the t distribution that you should know. Because हमने t distribution का कहा था ना कि it takes the same kind of shape which the normal density takes, right? Meaning standard normal density, which means ke centered at 0, a bell shape symmetric around 0, right? So that's how the density function of a t random variable looks like. That's what a t distribution is. तो इसमें और standard normal में फिर क्या फर्क हुआ? उसकी shape भी तो ऐसी है. क्यों जी? ये सवाल है ना? So standard normal जो है आपकी where the mean is 0 and the variance is 1, उसका density function अगर draw करेंगे तो वो ऐसे ही नहीं होगा. Anyone who knows what's the difference between the density function of a standard normal and the density function of a t?
Sir, I'm not sure, but I think the variance one होगी उसमें standard normal में इसमें variance फर्क है.
Sorry, आप क्या कह रहे हैं कि variance फर्क है?
जी sir.
Yeah, so I wouldn't put it like that. You are on to the right track, although जो standard normal है उसका भी इसी तरह का symmetric bell shaped curve है centered at 0. So shape दोनों की density functions की same है. The only difference is कि जो t distribution ये वाली जो है और जो standard normal है, standard normal has slightly thinner tails. So t distribution has thicker tails than the standard normal density. So अगर मैं standard normal density को भी इधर draw करूं, so I would have something like this, right? So बड़ा minute सा फर्क है दोनों density function में. In fact, the t distribution, as you know, t distribution has again a degrees of freedom parameter. इसका भी एक ही parameter है. So as the degrees of freedom approach infinity, as this parameter becomes larger and larger in value, what happens to the t density function? Basically, it starts to look more and more like the standard normal. As its degrees of freedom go to infinity. So आपने वो t table देखा होगा, उसके अंदर degrees of freedom are coming on the left hand side of the table. Each row is a different degrees of freedom. और उसमें bottom row पे infinity sign डला होता है. वो bottom row actually standard normal की आपको दे रही होती है values, because the t distribution converges to the standard normal as its parameter becomes really large. Okay. Any questions so far? You guys are really quiet. I'm kind of worried. What's going on? Okay. Minahil, do we have a quiz today?
Sir, yes, we have a quiz.
Achha, so let me just talk about one other density function and then
ठीक है.
we'll go for the quiz.
ठीक है.
So this is the last one. And this is the one that we are going to use next in our hypothesis testing. So this is called, so there's something called the F distribution. So what is the F distribution? Don't ask me what F stands for, because I don't know. But it is again a ratio of two random variables, where the numerator is also chi-squared and the denominator is also chi-squared. So, yeah, so chi1, chi2, and they're divided by some constant. Actually, degrees of freedom se divide after. So it is just a constant. So what does this density function look like? A ratio of 2 square root of chi-squared. Again, it looks very much like the chi-squared density function in that it only takes positive values and it is asymmetric. It thins out as you go further along. ठीक है जी. So that's the final sort of thing that we wanted to talk about, the normal density. There are a whole family set of distributions related to the normal distribution. Which is chi-squared, T, and F. Okay, now we can stop and take a quiz and come back quickly because we think after. Minahil, actually quiz को skip ना कर दे.
Sir, कर देते हैं. I don't mind. ठीक है.
Okay.
Sir, also Vaji has a question. He has his hand raised.
Oh, G, Vaji. Sorry, I can't see raised hands.
Sir, is there, could you please tell us the point
By the
of
way,
using
if I'm
the
sorry, can I just say, if I'm on the board and you have a question, you can just unmute yourself and go ahead because I don't see raised hands. G.
Okay. So could you tell us the point of using a t-test over like a chi-square test or like a normal distribution?
Oh, so we haven't talked about a chi-squared test as such. We have talked about a chi-squared random variable. How it is defined, how is it related to a normal random variable? It is a function of a normal random variable, how it's related. So there's no chi-square test as such, जो हम यहाँ पे study करें. There is something called an F test that we are going to talk about now. अभी तो हम simply बात ये कर रहे थे कि just like there's a random variable, there's a family of random variables called the normal distribution, where you could have different means and variances and you get different density functions for your random variables. There are other families of random variables which are linked to the normal family, right? So if you have a normal random variable, you can square it and you will get a chi-square distributed random variable. If you have a standard normal and you divide it by a square root of chi-squared, you get a random variable which will follow the T density function and so on.
So how is the T density function more useful?
उसको तो हमने यूज किया है ना. अभी हम जो T टेस्ट कर रहे थे उसकी significance level की corresponding जो critical value हमने कहा, so that t statistic that we were creating followed a t distribution. So हमें 5% significance level के लिए हमारी critical value क्या होनी चाहिए, rejection region कहाँ होगा उन tails में, वो हमें t table से पता लगता है ना. या अगर हमने p value उसकी calculate करनी हो तो वो stata will use a t function because that t statistic follows a t density function, t distribution. So I mean there are two things. One is the test statistic. What is the formula you are going to use to test this particular null hypothesis? That is the test statistic. Confusingly उन दोनों का नाम t हमने रख दिया. The other thing is the distribution that that test statistic takes under the null hypothesis. If null hypothesis is true, what distribution is taken by this formula, right? That density function. So उस test statistic को भी हम t कह रहे हैं और उसका density function जो है उसको भी हम t distribution कह रहे हैं. So that can confuse you, but these are two different things. One is the formula, the statistic, how you are going to test that particular null hypothesis, and the other thing is what density function it takes, what is the distribution it takes, assuming null hypothesis is correct. And then related to that कि what is the distribution it takes, उसमें फिर ये भी है कि उसकी density function की equation क्या है, उसके नीचे area अगर हमने find करना है तो obviously उस density function को integrate करेंगे हम within some interval. तो integrate करेंगे तो उसका result क्या आएगा, all of those things. So those are like the technical details which we don't need to go into. There are statistical packages can do that for us. But we need to at least know कि उन density functions की shape किस तरह की, और हम अगर वो rejection region define कर रहे हैं तो वो density function की एक tail है या दो tails हैं, और वो हमारा rejection region अगर दो tails हैं तो उनमें से एक tail में है या दोनों tails में है. So उस तरह की चीजें we need to specify. But वो जो density function है उसका exact formula क्या है और उसको integrate करके क्या result आएगा, that for that we have t tables, we have tables, or we have access to these softwares which can do that for us. Okay. All right, I'm just going to give you the basic idea. There are examples in the book, and there are details there that you can read. It's not if you have understood t statistic use करने में हम क्या logic use कर रहे हैं और किस तरह से we are going about making that decision कि हमने reject करना है या नहीं reject करना. The same, a similar kind of logic applies here. So the basic apparatus, वो जो मैंने I posted a Word document on Teams yesterday, which gave 5 steps that we follow in any kind of hypothesis testing. Those same 5 steps apply here. So underlying logic जो है hypothesis testing की वो बिल्कुल same है, चाहे आप t test use कर रहे हैं या f test use कर रहे हैं. But because it is a different statistic used to test different kinds of null hypotheses, so we just want to talk about the differences. We are not going to talk about the similarities in the time that we have. Okay. So as I said, we could have a regression model, a multiple regression model, where we are interested in asking, so there is some, I could estimate, I have data on y and x variables. I use OLS, obtain a set of beta hats, beta coefficient estimates, and their standard errors. I now want to ask, is my regression model any good? Right? I've got some R squared, right? Which is a goodness of fit measure. Let's say R square equals 0.08. Right? So I want to, so the question I have is, these are my sample estimates, right? What is the relation among this set of x variables and y in the population, right? So population parameter की value, and the extreme hypothesis that I want to test is कि population में इनमें से किसी variable का कोई relation नहीं है y के साथ, which means that the slope coefficients are all equal to 0 in this regression model. So I just estimated a totally useless model. Sample में तो कुछ estimates मेरे पास आ गए, positive, negative, but in the population these variables were not related at all with the y variable. So what is the null hypothesis in that case? So that is called a test of model significance sometimes. So model significance test क्या है? कि मेरा model, regression model statistically significant है या नहीं? Taken together, these x variables, whether they have any correlation with y in the population or not. So the null hypothesis is beta 1 equals 0 and beta 2 equals 0 and so on up to beta k is equal to 0. Right? इसको आप इस तरह भी लिख सकते हैं कि all slope coefficients are jointly ना भी लिखें, all आ गया 0 in the population. Okay. What is the alternative of this null hypothesis? And so alternative hypothesis typically not hota na, of the null statement. So what's the opposite of this statement? Anyone?
Sir, all beta coefficients are not equal to 0.
So you mean if I were to write it like this in full, I should write beta 1 is not equal to 0 and beta 2 is not equal to 0 and beta 3, all of them are not
No,
equal.
sir, not necessarily. I think and का मतलब है कि इनमें से एक भी if it's not equal to 0, तो फिर the null hypothesis does not stand.
कौन से एंड का मतलब है? इस एंड का मतलब तो ये है कि ये भी 0 है, ये भी 0 है, ये भी एंड ये सारे 0. मैं पूछ रहा हूँ कि H1 में क्या आएगा? एंड आएगा और आएगा, क्या चीज आएगी? आपने कहा था ना कि all of them are not 0. Sorry?
I think और आएगा.
Or आएगा. Yes. So because if any of these, because we are making a strong claim in the null hypothesis कि वो सारे के सारे 0 के बराबर हैं. So if any one of these beta coefficients is non-zero, that goes against the null hypothesis, right? So we can write the alternative as beta 1 is not equal to 0 or beta 2 is not equal to 0 or includes both of them being non-zero as well, right? But we need just one of these beta coefficients to be non-zero. In words, अगर आपने लिखना हो तो you can write it as at least one slope coefficient is non-zero. One or more. At least one का मतलब implicity है. One slope coefficient is non-zero. ठीक है जी? So that's the hypothesis that we want to test. Okay. How would we test this hypothesis, this null hypothesis? So you might think, okay, easy peasy, इसमें क्या मसला है? मतलब we can have a t statistic for beta 1 मतलब individually हम already वो कर रहे थे in the example that we had where log wage was regressed on education experience and tenure. तो हम individually तो हर coefficient के लिए zero null hypothesis test कर रहे थे using t stats, right? So why can't we use a t stat for beta 1, a t stat for beta 2, and a t stat for beta k, all of them? So that's the only method we know. So उसको apply कर दें इस पे. तो अगर उनमें से कोई भी t stat significant आ जाए कि मतलब we reject the zero for this beta coefficient, that will mean that we are going with the alternative statement, at least एक beta coefficient तो non-zero है. So actually that's not a correct way of testing such a null hypothesis. So एक तो ये चीज है, which is important to keep in your mind. Cannot use the t statistics to test this H naught. इसका y थोड़ा complicated है, technical है. Just take that as a given for now. So if when cannot we use a t statistic? When our null hypothesis has joint multiple, more than one restriction. ठीक है. So जब तक null hypothesis simple था, सिर्फ एक ही restriction हम impose कर रहे थे, so that one restriction could be alpha plus beta equals 1, but it's still just one condition, right? कि उनको sum करें तो वो 1 आए. So one restriction हो null hypothesis में t stat is fine, go ahead and use it. But अगर एक से ज़्यादा restriction है, जैसे यहाँ पे how many restrictions do we have? So we are requiring कि ये वाला coefficient भी 0 है, ये भी 0 है, ये भी 0 है, ये भी 0 है, ये भी 0, right? So we are imposing a total of k restrictions under the null hypothesis, right? So if you are testing a null hypothesis which imposes more than one restriction on your beta coefficients, on your model parameters, you cannot use a t statistic, even though it might look like a simple exercise to go ahead and use t. It will give you incorrect answers. A t stat is only for testing single restrictions on your model. So what should we do? We should do something. We should use a different test statistic, which is called. Actually, there are more than one test statistic for a situation like this. But the one that we will learn is called an F statistic. What does it look like? What's the formula for the F statistic? So the formula now looks really complicated, so brace yourself. So it involves the sum of squared residuals. Actually, there are different versions of this formula. So book में आप देखेंगे कि r squared भी use कर सकते हैं आप to calculate the F star. But let's use the residual sum of squares. So, and there are two models that you are going to have to estimate. एक तो ये model है ना, regression model that you have estimated. You will need to now estimate a second equation, regression equation as well. So there's a residual sum. So this is called the unrestricted model. This is the model which does not impose the null hypothesis restriction. There's no restriction. I just minimize the sum of squared residuals without imposing any restriction on what the beta coefficient values could be, right? If I actually impose, instead of doing that unconstrained minimization of sum of squared residuals, if I do a constrained minimization, if I actually impose these restrictions, the null hypothesis restriction, that will be, we could also do that, right? So that is that's going to be my second regression that I estimate. So I'm going to estimate, so this is model number 1. unrestricted model, then actually let me write the regressions first. Then I'm going to run another regression, which we call the restricted model. Where I actually incorporate the null hypothesis restriction in my model, in my regression equation. So अगर मैं इनको incorporate कर लूँ तो मेरा regression model क्या हो जाएगा? It will change obviously, right? So अगर ये सारे beta coefficient 0 हैं, तो मेरी regression equation simplify नहीं हो जाएगी? I don't need to have these. I don't need to ask data to regress y on x1, x2, xk. I can simply say regress y on a constant, because ये सारे तो drop हो जाएंगे if their coefficient. If the null hypothesis is correct and all of these slope coefficients are 0, if these variables in the population are all unrelated with y, then my model does not need to include them, right? I can simply regress y on beta 0, right? So my restricted model will not have any explanatory variable. So that's a restricted model because it incorporates the null hypothesis restrictions on my model. So it says, okay, let's take that as correct and let's impose that restriction. Let's not put these x variables in my model, right? So data ke andar, you might be thinking, how can you just not have an x variable in your model? You can. So data ke andar, you can say regress just a y variable without giving any x variable names, and then it will report an estimate of beta 0. Intercept to wo fir bhi estimate karega. Unless agar aapko intercept nahi chahiye, so then you say in a regression, if you don't need an intercept, you say comma no cons. I don't need the constant term. Put the constant term equal to 0. Again, you are imposing a restriction on that minimization, least square minimization. You are saying minimize the sum of square residuals, but I want beta 0 hat to be equal to 0. I'm just putting that restriction. So anyway, we do want the beta 0 to be there for this purpose. And so that's my restricted model. So इस model को estimate करने के बाद हमारे पास data will tell us sum of square residuals. So RSS इस model का भी आएगा हमारे पास. We call that RSS unrestricted. इस model को जब हम estimate करेंगे, again data will, after estimating beta 0, it will give me an RSS, the sum of squared residuals, which we residual sum of squared, which we call RSSR for the restricted model. Which of these two RSS will be larger than the other? Anyone?
Sir, unrestricted का larger नहीं होगा?
RSS unrestricted will be greater than the RSS from the restricted model. Why?
Because there are a lot more variables in there.
In the error term? In which model? In the first model or the second?
In the first one. So there's going to be a like.
Oh, there are a lot more variables in my model. अच्छा ठीक है. तो उससे क्या होगा?
Sir, residual शायद ज़्यादा. Because residual is the difference between the actual value and the expected value, right?
The residual is the difference between the actual y value and not the expected, the predicted y.
And the predicted
value. जी, yes. So उसका sum of squared residuals हम ले रहे हैं, तो आप कह रही हैं कि पहले मॉडल का जो sum of squared residuals है वो बड़ा होगा दूसरे वाले से?
Yes, sir. Maybe, I don't know.
I think it wouldn't it be the other way around? Anyone who thinks it will be the other way around?
जी सर, it would be the other way around, क्योंकि restricted model के अंदर में prediction जो होगी, it will be काफी loose prediction होगी and it won't be accurate as it would be in the multiple linear regression model. I think so.
Yeah. Actually, it is the other way around. So unrestricted का sum of squared residual is smaller than the restricted model sum of squared residual. इसकी दो तरीके से आप इसको सोच सकते हैं. Why that would be the case? One is like you were saying कि in this model we are trying to explain हमने कुछ x variables तो डाले हैं ना. So if you think about this, this part gives you y hat, and what is left over is the residual, right? So this regression is breaking y into y hat and u. यहाँ पे भी y hat आ रहा है, but वो एक constant है, और then you have it. So और फिर sum of squared y hat को हम explained sum of squares कहते हैं, इसके sum of squares को हम residual sum of square कहते हैं. तो इस मॉडल में we are putting some variables to try and explain some of the variation in y. Unless सारों के coefficients खुद ही 0 आ जाएं, we will get some explained sum of squares, right? So we will be able to explain some portion of the y variation in this model, but not in this model, क्योंकि इस मॉडल में तो कोई explanatory variable आपने डाला ही नहीं, तो आप एक simply एक constant flat line एक तरह से fit कर रहे हैं. तो उसने क्या variation explain करनी है भाई? So the explained variation in this model is going to be much less than the ESS in this model, and the other way on the RSS. So the residual, so all of the variation in y is going to be in the residual. So RSS is going to be larger here than it was over there. दूसरा तरीका, so ये तो intuitive है. Another way to think about this is that this is the if you so हम minimize क्या कर रहे थे? In OLS we try to minimize the sum of squared residuals. So we want to pick beta hat values which minimize the sum of squared residuals. So RSS is like the value of the objective function at the optimum point that this minimization finds, right? So in model 1 we had the unrestricted model. We were minimizing the sum of squared residuals without imposing any restrictions. This model can be thought of as a constrained minimization. So हम इसी को minimize कर रहे हैं, but subject to beta 1 and all of those. So imagine having the same objective function as this model, but imposing this constraint on it. That's what we are doing in model 2, right? So the outcome from this, you can think of this as a local minimum or a constrained minimum, and the outcome from this model is like the global unconstrained minimum. So जो global minimum है, जो unrestricted model की value है objective function की at the optimum, that's going to be always less than equal to the local or the constrained minimum, right? So that's another way to think about why this will hold. And now let me give you the formula for the F statistic, because it is comparing these two sum of squared residuals. Let me write it over here. So the actual formula looks quite complicated, but don't be intimidated by it. So as I said, F stat has, again, like the T statistic, it's a ratio, but it's a much more complicated ratio. So in the numerator, we have the RSS of the restricted model minus the RSS of the unrestricted model divided by number of restrictions in the under the null hypothesis, which are k. So total number of restrictions imposed. And then in the denominator, so in fact the numerator is also a ratio. So ye difference divided by k, and then the denominator is the RSS of the unrestricted model divided by the degrees of freedom in the unrestricted model. which are simply n minus k minus 1. अगर आपने उसको पूरा लिखना है तो n minus k plus 1, where k is the number of x variables plus c. ठीक है जी, या n minus k minus 1, remove the parenthesis. This becomes minus. Okay, so so you calculate this and you can show that this is using the arguments that we just presented, that this follows an F distribution, this statistic under the null hypothesis. Assuming H naught is correct, it follows an F distribution. Okay. So therefore, if we want to test this hypothesis at 5% significance level, we will need to go to an F table, because what we want to do, और F density function मैंने अभी आपको दिखाया था, draw it over here. That's an asymmetric, that looks like a chi-square. So 0 से start होता है density function and then it goes like this. So अगर मैंने 5% rejection region रखना है इसमें, obviously इसकी एक ही tail है, उसके अंदर आएगा 5% area. So the critical value I need to read from the F table is the value which corresponds to an area of 0.05 in the table. इसकी actually degrees of freedom भी होती हैं, just like the so अगर F table आप देख रहे हैं तो आपको df1 df2 so degrees of freedom are really straightforward. ये जो दो चीजें हैं, ये basically degrees of freedom. So ये वाली numerator degrees of freedom है, पहले आती हैं ये denominator है. And so if your F statistic value falls in the shaded area, we reject H naught, which means that at least one of the beta coefficients is non-zero in the population. If the F statistic this ratio falls in the unshaded area, meaning that it is kind of close to zero, not that far away from zero, then we do not reject H naught, which means we are concluding that none of these X variables are actually related with Y in the population. Okay. Okay, we are out of time. But those of you who can stay, or if those of you who have a question. So the lecture is finished, but if you have any questions. Oh, by the way, there was a mutiny going on Teams. Apparently